All right, this is part 3 of material testing. So here's our stress strain curve. You'll recognize that this looks very similar to our load versus displacement curve, but in the last video we were talking about the relationship between stress and load and strain and change in length or deformation. So now this is a stress versus strain curve, and what that does is that eliminates the variability when you have different test samples. Now, regardless of the size of the test sample, if it's the same material, we're going to get the same type of curve. And so you more often see a stress versus strain curve than a load versus displacement curve. So we need to talk about the different parts of this curve. You'll notice that this first part of this curve is a straight line, and that is what's called a linear response, or if I apply a certain load, I should expect to get a certain amount of deformation. If I apply a certain amount of stress, I can expect to get a certain amount of strain. So that region is called the elastic range. It's called the elastic range because if I apply a load, say I apply a load up to the middle of this elastic range, if I were to let go of that, I'm going to see that the test sample, returns to its original size, original position, original shape. Think about a rubber band in this case. So if I stretch out a rubber band and I let go of it, I'm likely going to see that it goes way back to its original shape. All of these, everything that's been designed is designed to operate in this elastic range. What we see is that we might have loads being applied to whatever it happens to be. If it's a car part, if it's a airplane part, whatever it happens to be, it's all going to be loaded in this elastic range. It's not going to get beyond this point. We don't want it to get beyond this point. We'll talk about what happens up here in a little bit. So this is called the elastic range. This idea of a proportional limit, what that is that's the end of this straight line. So proportion means that we're going to have a proportional return. So a proportional return for the amount of stress that's being applied. We're going to get a proportional amount of strain out of it. So the next part of this is what's called modulus of elasticity. We saw this when we were talking about beam deflection, when we were standing on our pieces of wood. This was a term related to the material. And we found that every material has what's called a modulus of elasticity. Well, what that is the slope of this line right here. So the proportional constant says ratio of stress to strain. So we have this equation, modulus of elasticity, big E, equals stress over strain. Again, remember that every material has a modulus of elasticity. I'm going to see something that's very, very strong, like a steel, is going to have a very high modulus of elasticity, while something that may be relatively weak, like a rubber or like a plastic, may have a lower modulus of elasticity. And so this is just based on how much stress and how much strain, or how much strain comes out of an applied stress to that test sample. So that's called modulus of elasticity. We'll remember that for later. What it is, it's a measure of stiffness. So the greater the modulus of elasticity, the stiffer the material is going to be. Again, the relationship between steel and rubber, we're going to see that steel has a very high modulus of elasticity. Rubber has a relatively low modulus of elasticity. So notice the animation here. So if I apply a load and I release it, it's going to go back to its original size. So we could do this with a test sample. We could apply a load up to a certain point, and if I released it, I should expect that this test sample goes back to its original size. In theory, you could do this forever, and it's always going to come back to that original size. Another term for the top of this straight line is what's called the elastic limit. Kind of makes sense. It's the limit at which the elastic behavior happens. When I get beyond this, I'm going to get into another region we're going to talk about here in a second. But the elastic limit, what that is that's the point at which elastic behavior stops. Notice it says elastic and proportional limit are almost identical, with the elastic limit being slightly higher. what we're going to find is that there's a lot of information, there's a lot of names for this point right here. So resilience, the idea with this is we have an amount of energy that is withstood by a material. And basically, resilience is the area under the stress strain curve. So we're looking at how much energy can be absorbed by this material. So it says, why would this be important? Well, we could think about something that can absorb a lot of energy, like a car bumper. So maybe not necessarily that it has to be a real steep stress strain curve, but just that there's going to be a lot of area under here represents a resilient or tough material. Again, here's a third point at the top of that straight line. And this is what's called the yield point. So now what this is talking about is this is talking about the point when the elastic limit has been exceeded. So this, in theory, is a little bit beyond that elastic limit. This is the point at which, when I start stressing it to this point, I'm going to get behavior, or I'm going to get elongation that cannot be returned. So it says a very small increase in stress produces a much greater strain. So kind of recognize what's going on here. So we have a proportional return here, but as I get beyond this, what I'm seeing is if I apply a little more stress, I'm getting a lot more strain. So I'm getting a lot of movement for not a whole lot more stress. So this is pretty consistent regardless of the material. You're going to get into this region, but it's going to start at this yield point. Again, here we are at the top of that curve again. What this is saying is this idea of offset yield strength. What this is we can't really identify the point at which this straight line turns into this curve. It's often very difficult to exactly point out where that is. So what we're looking at here, this offset yield strength, this is the point at which we can positively identify that that a tolerable amount of permanent strain has occurred. So we can see that this has actually happened. So this first part is what's called the elastic range. Now, when we get beyond this point, our yield point or our elastic limit, we're getting into a region which is called the plastic region. So this is the region at which, when I apply a stress beyond this point right here, I'm going to see that I'm not going to be able to recover this deformation back. It says unrecoverable elongation beyond the elastic limit. When the load is removed, only the elastic deformation will be recovered. So what that means is if I apply a stress to this point, I'm going to recover all of this strain from here down, but the strain from here to the point of application, I will not get that back. Great example of this would be like a piece of plastic, like a plastic fork, for example. So I can use that plastic fork and I can bend that a little bit back and forth, back and forth, back and forth. But once I bend it beyond the point at which it kinks, I have now exceeded this yield point. So regardless of whether I want to try and bend that back or pull it back to its original shape, I'm never going to get it back because that kink in that fork, that has exceeded this yield point. So I may have gone way up here into this stress value to where now when I remove that force, when I remove that load, I'm going to see that it's never going to go back to its original shape. So I've gotten my elastic deformation back, but I have not recovered my plastic deformation. So again, elastic, plastic. All right, so onward we go. So anytime I'm in the plastic range, that's considered failure. So I've gotten beyond the point where I can recover my original shape. So it says part dimensions will now be outside of the allowable tolerances. So if I apply a force right up here, I'm going to be stretching my piece, my part, just that tiny little bit. And so now when I want to have it go back to its original shape, I'm going to see that it's just a little bit too long, which is not okay. So any place in here, any point up here represents failure. So we need to kind of talk about what failure is in a little bit. So deformation, it says this is the point at which the test sample is elongating. So I would kind of ask you to remember back to that video, and you saw that we stretched and stretched and stretched, and before it started necking, what we had is we had a region at which we saw a lot of deformation. It stretched really, really far relatively quickly. So this deformation region, we're actually getting quite a bit longer over this period here. And it says the cross-sectional area decreases. So think about the test sample that we have. We have a defined volume of that cylinder. We had an original length, we had an original diameter. I could calculate the volume of that material. But now, as I got a much longer cylinder, I should have a corresponding smaller diameter to that test sample. So it says cross-sectional area decreases. Corresponding to that, it says the load-bearing ability increases. Well, let's think about that. If I have a load that's being applied right here and a smaller cross-section, remembering that stress is load over area. Well, if I have a bigger load in a smaller area, I should expect that my stress is going to actually increase quite a bit. And so my load bearing ability increases because my cross section decreases. So the material is getting stronger because as I'm pulling on that, what I'm going to see is that the grains of that test sample are actually aligning to each other. And so this is called work hardening. And so as I'm pulling on that, I'm actually making that material very, very strong. But again, remembering that as I'm pulling on this, I'm actually deforming it beyond the point at which I can get that deformation back. All right, so the weakest point is stretched and now becomes stronger. So now it's going to keep getting stretched. And this point right here, and you saw this on the video, this point at the very top here is what's called the ultimate tensile strength. So the load-bearing ability peaks, and now this region right here starts to form, and this is what's called the neck. And in theory, this whole cylinder has a consistent cross-section, but at one point along this cylinder, there's going to be a point at which there's either a defect or there's a nick or something that creates a weak point. And what will happen is that's the point at which this neck will occur. Once that neck occurs, it's not going to keep stretching anything out here. We're going to see that the deformation is going to be occurring only in this region. As I pull farther and farther and farther, this neck is going to get more and more pronounced, more defined. So failure, again, we had talked about failure, so any point in here is failure. But if the continued force is applied, necking will continue until fracture occurs. So again, notice failure versus fracture. Fracture is the point at which it's in two pieces. So fracture is at the end of the curve. Failure occurs anytime I get into this plastic region. One term that's associated with failure and associated with fracture is what's called ductility. And what ductility means is how long is this plastic region of my curve. The longer this curve, the longer this region, the higher the ductility of the part. The shorter, what that is that's a very brittle type material. So we can think about this with different types of material. We could think about glass versus like a rubber. Glass is going to have a very low ductility. We're not going to get a whole lot of strain out of glass. Conversely, I'm going to get a tremendous amount of strain out of rubber. What I will see is that the rubber is much more ductile than glass. Our next video is going to focus a little bit on what fracture looks like with different types of materials and some related tests.